Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. We have worked with derivatives for quite a while now, but every single function we have differentiated has been formatted the same way. It's always y is equal to something, or f of x is equal to something. These are what we call explicit functions because y is explicitly defined in terms of x. It's nice when y is already isolated for us, but the universe isn't always that nice. Sometimes x and y are mixed together in a messy relationship. Today, we're going to learn something called the implicit differentiation. This is the tool that lets us find the slope of a curve when we can't, or don't want to, isolate for y first. Now, before we dive in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. We're going to introduce implicit differentiation by looking at this equation of a circle here. So first, we're going to find the derivative explicitly. And this is what we've always done. So we start with by isolating y. Moving the x squared over to the right-hand side is going to give us y squared is equal to 25 minus x squared. And then we're going to take the square root of both sides. So we end up with y is equal to positive or negative square root of 25 minus x squared. Okay, so now that we've isolated y, we can go ahead and find the derivative. And to do that, we're going to need to use our chain rule. So let's actually go ahead and rewrite this so that we can see the composite function more clearly. So this is plus or minus, and we have 25 minus x squared to the power of 1/2. So then we get y prime is equal to, we have our plus or minus, and then our outside function here is that to the power of 1/2. So using power law, we get this is 1/2. And then we're going to keep our inside function exactly as is, which is 25 minus x squared. And then this is now going to be to the power of negative 1/2. And now we need to multiply this by the derivative of our inside function. So the derivative of 25 minus x squared is negative 2x, which means y prime is equal to plus or minus negative 2x over 2 times the square root of 25 minus x squared. And then simplifying this a little bit, we end up with this is negative or positive x over the square root of 25 minus x squared. And this is where we would usually stop. Next, we're going to take a look at differentiating this, but we're going to do it implicitly. So when we find the derivative implicitly, we don't need to isolate y. All we have to do is take the derivative with respect to x on both sides of this equation. So that means we're going to take d by dx of the left-hand side, which is x squared plus y squared. And this is going to be equal to the derivative with respect to x of the right-hand side, which is 25. So the important thing to note here is that y is still a function of x. And you'll see why that's important later when we take the derivative of the left-hand side. So now for the right-hand side, the derivative of a constant is just equal to 0. And then for the left-hand side, when we take the derivative of x squared plus y squared with respect to x, well, for the first term, derivative of x squared is going to be 2x. And then we add, now the derivative of y squared is going to be 2y. But the fact that y is a function of x, you can almost think of it as y squared is a composite function. Our inside function is y, and the outside function is squared. So here we need to apply our chain rule, which means the derivative of y squared is going to be 2y multiplied by the derivative of y with respect to x. So that is going to be dy dx. And now moving 2x over to the other side, we get 2y times dy dx is equal to negative 2x. And now we just need to isolate dy dx. So we get dy dx is equal to negative x over y. Now let's go back up top to see where we differentiated it explicitly. So here we had negative or positive x over the square root of 25 minus x squared. But notice that y is equal to positive or negative square root of 25 minus x squared. So we can actually go ahead and substitute that in, and this is equal to negative x over y. So it is actually the same thing. It's just that here we had it only in terms of x, and then when we differentiated implicitly, the derivative was expressed in terms of both x and y. So notice how when we did the derivative implicitly, it was much faster, and it allowed us to perform algebraic moves with y. Let's take a look at another example. Here we want to find the derivative of sine y plus x squared times y cubed is equal to 10. And here there's no way for you to isolate y. So the only way for us to find the derivative is to use implicit differentiation. Now implicit differentiation says that we're going to take the derivative with respect to x of the left-hand side of the equation. And then we're also going to take the derivative with respect to x on the right-hand side of the equation. Again, it is important for us to know that y is a function of x. So same thing, on the right-hand side, the derivative of 10 is just equal to 0. Now on the left-hand side, the derivative of sine y, we're going to have to use our chain rule, because remember, y is a function of x. So the outside function here is sine, which means we're going to get cosine y. And then we're going to need to multiply this by the derivative of the inside function. And the inside function here is just y. So the derivative of y is dy dx. Next, we're going to add the derivative of x squared times y cubed. So here we need to do our product rule first. So that's going to be 2x times y cubed. And then we add that to x squared times the derivative of y cubed, which is 3y squared. And then again, chain rule means we need to multiply this by dy dx. So now when you're doing implicit differentiation, we don't care about the terms with y. All we care about is we want to isolate dy dx, which means here we're going to group the terms with dy dx on one side and then all the terms without dy dx onto the other side. So we have this term that has a dy dx, and then we have this term that has a dy dx. So these are going to stay on the left-hand side, which means we get cosine y times dy dx plus 3x squared y squared times dy dx, and this is equal to negative 2x y cubed, which is us moving this term over to the other side. And now we can go ahead and factor out the dy dx from both of those terms on the left-hand side. So this would be dy dx multiplied by cosine y plus 3x squared y squared. And that is equal to negative 2x y cubed. And now all that's left to do is isolating dy dx. So we end up with dy dx is equal to negative 2xy cubed over cosine y plus 3x squared y squared. And that would be our final answer here. And finally, for our last example, we're going to talk about a curve named the Witch of Agnesi. And it can be defined by this equation here. And yes, while we can isolate y, we've learned that it's actually much simpler to differentiate implicitly. So let's just take a quick look at what the curve looks like. So we have y times x squared plus 4, and this is equal to 8. So it looks somewhat like a bell curve. And the question is asking us to find the tangent line at the point 2, 1. So we're looking for the equation of the tangent line at this point right over here. So we're going to use implicit differentiation and differentiate both sides of this equation with respect to x, which means it'll be d by dx of y times x squared plus 4, and this is equal to d by dx of 8. So for the left-hand side, we're going to use our product rule because we have y, and then we have times, x squared plus 4. So product rule says we're going to take the derivative of y, so that'll be dy dx. We're going to multiply this by x squared plus 4. And then we're going to add y multiplied by the derivative of x squared plus 4, which is 2x. And this is equal to 0. So here we can go ahead and isolate our dy dx. So we get dy dx is equal to negative 2xy over x squared plus 4. Now the question is asking us to find the tangent line at the point 2, 1. So we've already been given our point. Our point is 2, 1. So we just need to use that to find the slope at that point. And since we have dy dx, all we need to do is substitute in our x value and our y value. So this means dy dx evaluated at the point xy is equal to 2, 1, that is going to be negative 2 times 1 over 2 squared plus 4. And this works out to be negative 1/2. So this here is going to be our slope. And now that we have a slope and a point, we're ready to write down the equation of the tangent line. So using our point slope form, we get the equation of the tangent line is y minus 1 is equal to negative 1/2 times x minus 2. And this would be the equation of our tangent line at the point 2, 1. And now let's do a quick recap of what we covered in this video. So the idea of implicit differentiation is that it allows us to find the slope of curves where x and y are mixed together without the need to solve for y first. And this is very useful because a lot of the times it's difficult or maybe even impossible for us to isolate y. And the technique here is to differentiate both sides of the equation with respect to x. But you must always keep in mind that y is still a function of x, which means every time you differentiate a y term, you need to apply the chain rule and multiply by y prime, or in other words, multiply by dy dx. And once you've differentiated, our goal is to isolate dy dx, and it can be in terms of both x and y. And now it is your turn to give this a try. Can you find the derivative of the equation on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.